So for full disclosure, I'm neither a physicist nor a machine learner. I'm a statistician. So I normally work on non-stationary spatial statistics. But here I'll talk about a project I did at ENCA that actually doesn't involve spatial statistics. And hopefully I'll keep the stats light and still point out some aspects that I think might be relevant for this community. So I still hold a visiting appointment. I worked at ENCA for 7 years, if I remember correctly, in the stats and then later machine learning group. And a lot of the work we have been doing, I think many of you are very familiar with ENCA, but the group I was in was specifically in charge of, say that again? Okay, is this better now? Yeah. Okay, good. All right. So a lot of, I think many of you are familiar with ENCA, the National Center for Atmospheric Research. And the supercomputing center they run is called Cheyenne. There's about a new supercomputer in development right now. And a lot of the work that my group was charged in doing is actually making sure that the climate model runs correctly, which is a broadly defined term in these different HPC environments. So this is just a sketch here. Obviously, this is a community. You're very aware of how complex these models are. And one of the things that's maybe particular to the ENCA model, to CSM, is that there's a wide user group. So it's both the development, the type of people who use it is very large. Many universities install it, many centers around the world. So one of the things that was very important at ENCA is making sure that if the model is ported to other environments, that this is done in a way that is consistent with how the model is run at ENCA. And this is a little sketch here showing the development of the model and the different components that were added to the model through really maybe the last 5 to 6 decades here. And as we have heard through multiple times already today, the model is about 1.5 million lines of code. I actually just got an email. It's almost 2 million lines, depending on how you count it. Whatever the details are, it's a big fat code base. Most of it is done in Fortran, so that's also not always the easiest code to work with. And as here, this says the type of code or the way it's done is modern and maybe not so much modern. So there's a lot of legacy code in there. And yeah, give you also an idea about the number of modules and functions that are in there. And the idea is that also CSM is very scalable in the sense of it's supposed to run mainly on HPC infrastructure, but there are also smaller versions that run on individual laptops. And it's in a constant state of development. A lot of the work that's being done is actually recoding part of the code and turning it into GPU computations like we have heard. And all these kinds of things are something that where software quality assurance was a big part of that. So what we mean by that is, no matter which of these computational environments you run it and what computing infrastructure, what compiler you use, there shouldn't be any large differences as a result of making these changes in the computing infrastructure. So you would say, well, what's the big deal? Let's just run the model on one system and let's run the model on another system and just compare the results. So in IT language, you would say we would like that model to be bit for bit reproducible, meaning the output is exactly the same. That does actually hold if you run the model on exactly the same computing infrastructure, but this is a big if here. So all these things, like you want the same software, the same compiler flags, the same MPI library, so all this kind of nonsense sunk in that we really don't like to think about, but that actually turns out to really matter, even down to things like using the same random number generator. So for most practical cases, this is clearly not the case. So we're usually interested in saying something meaningful about how the model runs if these conditions are not met. So we're interested in optimizing the code, new hardware technologies for different compiler flags and things like that. So the question here, to state this very simply, is, so now if the original output and the new output, after we do this kind of change where we don't expect anything to change in the actual scientific content of the data, how can we evaluate that these are actually correct, or correct? I frame this in quotes here. So we know we don't expect this to be exactly bit for bit reproducible, but how can we still say something about them being the same? And in climate terms, what we heard a lot from scientists is what they really care about. Is there anything that changed the climate? So the key question here is, do any of these different these computational settings cause the output to be climate changing? And that's a tricky question, because what do we actually mean by climate changing? So there is no clear definition. And it would be if we could clearly define this and say, well, 100 years down the road, the temperature shouldn't change by more than 0.1 degrees or something like that. Of course, we could code that up and have a software quality assurance like that. But in practice, we're talking about hundreds of variables being output, and you don't just worry about one thing. You know, so when we started working on this, we were trying to get a definition, but we really couldn't. So what was done in the past is that they literally ran these models out for 400 years, and then a smart scientist, like let's say Maria, would have been tasked with the job here. Please look at this output and spend maybe weeks there and look at all the little things, and does this still look the same? So short of that turning into snowball reverse or something, this is really not a non-trivial task. So what we were trying to do is something that's fully automated and can answer the same question. Easy to use and objective, I guess is what you see here. So something that I think many of you are familiar with thinking about is thinking about a random chaotic system in the terms of characterizing that through a large ensemble here. So what we did here is we literally changed the question. Instead of saying is it climate changing, we said, is the new data structurally statistically distinguishable from the acceptable large ensemble? Unacceptable, I'll put this under quotes here and talk about this a little bit differently here. So the idea is, in a broad sense, if you have an accepted ensemble, if you say, well, I treat these as being the truth in some sense, but I know this is a chaotic system, so there's a large variability in there. What can I say about a new run? Does that fall within that variability created or characterized through this ensemble? So that's the setup here. And giving you an overview here before I'll go into the details. So the idea of this testing framework is called Ensemble Consistency Testing. This is actually now has been part of the standard CESM releases for the last 2 years or so. So you might already have used it. The idea is that all the heavy lifting happens at anchor, so creating the large ensemble and statistically quantifying that variability happens on the software engineering end. So there's a large team that can do all this work here. Versus on the user end, the work should be very little here. So this is not, we're not thinking about it in the way that we say we want to create 2 large ensembles and compare them, but rather we are framing the problem where we say we have a large ensemble and we can put a lot of effort in making this really fancy and large. And we want very little work on the user end. So we want them to run as few new runs as absolutely necessary. So just some highlights here. So this is an automatic Python tool. It's very easy to use. It literally takes about, after if you have your new run, about 1 second to get an answer here. And the answer that we are wanting to get out of this is a pass or fail in the sense of, is it consistent, yes or no? Some of these details here. So now I'm going to go a little bit, how are we creating this ensemble, and also how have we changed how we think about creating this ensemble throughout the years here. So the idea here is that we use, again, on the code, an accepted machine software stack. In this case, that is the HPC environment at Anchor. There's no claim to say this is the absolute truth. No reason to say any of the other supercomputers would be any better. But because this model is developed at Anchor, that's what we go about here. We use this 1 degree, so this obviously you can do this on all kinds of different scales, but for reference here, all the work I show you is with the 1 degree model runs here. And we do the computations in the usual way, how they're always done, to create ensembles where you make these tiny, tiny changes in the initial temperature fields. We have actually done, if that interests you, we have done a lot of experiments where we trigger the changes to something else, like things like different compiler flags. And it's actually a fascinating topic by itself, how you can actually see it as a difference depending on how you grade the changes. I won't be talking about this here, but if that interests you, glad to catch up on that. There are about more than 200 variables. It turns out, so this is where it came in first, we thought we have to do this actually spatially so that we would actually do something more meaningful, but turns out you can actually completely average globally and you get all the signal you want, which was very surprising to me, but turns out that's the case. So when we started off, we did averaged 1 year simulations because we saw that a lot of the changes that people might be worried about, you should run the model for at least a year. Also turns out that's not necessary. So once you have this larger sample, so we have many variables. In this case, I've got over 200. So it's not trivial to compare these variables one by one. Apart from the statistical issues that you have with these multiple comparisons, also these variables are highly correlated. So if you don't account for this correlation, you have all kinds of troubles coming up with a correct hypothesis testing where you can actually derive specific properties of a test that you would like in normal hypothesis testing, then if you ignore that. So what we did instead, we said, well, let's work and do this comparison in a projected space using principal components. And I think we've already discussed principal components in yesterday in some of the talks with all these different terms. Again, you're used to calling it empirical orthogonal functions or something like that. So this is all the same term here. So the idea is we obviously need to standardize all the variables, and then we derive these principal components. That means we project into these orthogonal subspaces that maximize the variance. I think we're all somewhat familiar with this here. And then we compare and do this testing setup in these using the principal component scores. So those are these linear combinations of the original variables in these subspaces that are independent and orthogonal to each other. And the reason that's attractive from a statistical point of view is because we can work with that independence and actually derive theoretical properties of this testing framework here.
Sorry, the new runs are projected in the space that you're considering.
Correct. Yeah. So I'm going to talk about this in a little bit more detail at the end, where we look into the details here. But you're right. Yeah, exactly. We derive the principal components from the large ensemble, and then you do only a very few new runs. So in our specific setup, we use 3, but you could use 2 or 4, which would just change a little bit the exact parameters of the test. But you use the projection from the large ensemble. That's correct. Yep. Alrighty. So so what's the key here is that what really differentiates it from comparing variables one-to-one is that we pick up changes in variables. And that turns out to be somewhat relevant. Let's say you have an ensemble of 500 runs. There would be in individual variables, there would be a very wide spread, but how they can concur jointly is very different. And that allows this PCA type testing framework to pick up really subtle things, as I'll show you later here. So that is really the key underlying idea here, that we are not just testing variables individually, but we are really accounting for the relationships seen in these multivariate relationships seen in the large ensemble here. Okay, so the setup is, the null hypothesis is that we say the new climate simulations, they come from the same distribution as the ensemble simulation. Again, that's a very strong statement here. Yeah, we are really not treating the new ones the same as we treat the old ones. We say basically the large ensemble is the truth, and we're just interested in the question. We have now a small number of new ones to the fit within that high-dimensional space that we are getting from the large accepted ensemble here. And as you're probably all familiar with from hypothesis testing, there are usually 2 things we worry about. It's the false positive rate, and on the other hand, the power. So here you can see the definition here is if we are falsely rejecting the null hypothesis, if we are saying this new run is crap, do something about it, compared to the power is then the probability of correctly rejecting H0. So when would we actually figure out that the new one is wrong when it truly is wrong? So when you design this kind of tests, you always want to balance this. It turns out that we really didn't have to worry about power, to my big surprise, because as soon as something, we worked with a lot of scientists to give us things where they knew they were wrong. As soon as something was wrong, we had amazing signal strength. So when tiny little changes, they appear very strongly. So we really didn't worry about that too much, but we worried a lot about the false positive rate. But we didn't, clearly, if you have a testing setup like that, you don't want to tell people something is wrong. Then you have a lot of people trying to figure out what's going on if that's not the case. So we were very much in a framework of making sure that our false positive rate is as low as possible already. Let me show you. So quick setup here of what the procedure looks like. So what you see here on the left are all the new runs, and this F, we just use the term S here because those are these new scores. So these are these variables projected into these subspaces. And we picked 50 here because that explains all of the variability. You could, of course, do whatever fits with your specific setup here. And then we say, let's compare where these new runs fall, their distribution of their principal component scores compared to the distribution of the principal component scores of the ensemble. Turns out they're actually very nice connections to the eigenvalues of the original covariance matrix. I'm going to talk about that a little bit later in detail and why that actually matters and allows us to really establish the theoretical properties of this estimator here. And then once you have this, so you can say, you can think about this as a normal variable and say, does it fall within each individual PC score? Does it fall within this distribution? And then you can say yes, no. And you work your way through. And again, these details of the setups, that's something you could define differently. We used having 3 different runs and saying, once we have 2 principal component scores in that same score fail, we declare this a fail, which you can kind of see here as a sketch how that works. And then if we have more than 3 of these failing through the column, we get a fail overall. Again, these details of the setup, that's something one can very much adjust. We can all derive this theoretically. We did this specifically to get a false positive rate roughly in the setup 0.5. So how well does this actually work? Well, it has been in use now for quite a few years. And in the initial year, we did about, I want to say, over 100 different test case scenarios. So it works very well. So anything that scientists would expect to fail, it turns out it does fail. That says fail here. Anything we would hope it would pass, like little things like using a different compiler version or changing the code or things like that, it passes. So that's really good. So it was really difficult to find any errors. Anything but a model actually, but this kind of testing framework didn't work. So yeah, it has been used for quite a few years so far. Then one of the things though that we wanted to push is it's pretty cumbersome to create these 1-year runs. And as you'll see, you actually need quite a few. So we're talking hundreds of runs to get a stable estimate of this initial ensemble. So people were really interested in saying, well, now that you can show that 1-year runs actually work, could we potentially do something shorter? And turns out we can. And so obviously shorter is cheaper in terms of running it, and then people are also much more inclined to actually do it. And we wanted to investigate. So what we need here in this, we wanted to see how far can we go down where we still get a spread in these runs here to establish what the ensemble should look like. And what you can see here, these are 3 of these 200 plus variables that we show here. We show the initial time steps. I think they're shown here through the first 45 time steps, where 1 time step corresponds to half an hour in real time here. And we did some Dan Milroy. He was a PhD student in computer science, and this was mainly his thesis work. He has done a lot of work actually characterizing this, and it turns out at 9 time steps, we already have enough variability that the whole framework works really well. So you don't need to run it out for a whole year. 9 time steps is all that's needed. And of course, then we started redoing all this testing here with these 9 time steps. And they're almost always in agreement. Right? Again, hundreds of test cases where we can see whatever we can see in 1-year runs, we can already see in 9 time steps. There are two exceptions that we found and that I want to highlight because they're kind of interesting, where we have counterexamples. So one counterexample was changing one of the soil hydrology parameters. That's part of the land model in CESM. And that change truly doesn't propagate in the first 9 time steps because it takes a while before. So we are only testing the atmosphere variables here. So that's a case where the 1-year model does pick it up, the 1-year testing framework, but the 9 time steps doesn't. So that's something to be aware of. There's something in one of the other modules that goes through the coupler and it truly hasn't propagated. It's good to be aware of. So it's in some ways, it's a trivial counterexample, but still important to know. This one is actually much more interesting. That is changing the random number generator. That's an example where the 1-year runs look all good as they should, right? We would not hope that changing the random number generator per se would truly change what the climate looks like. But it turns out in the 9 time steps, we can systematically pick that up. So you can really see in the first 9 time steps that there's a systematic difference between runs from one random number generator compared to using a different one. So I thought that was pretty fascinating. That wasn't something I would have expected. Alrighty, so we have, so overall here, maybe it would be fair to say now the way this is done is that the fast one, the ultra is called UF is ultra fast, so that 9 times the one is the one that's practically in use. And only if you get a fail, then you also run the 1-year run and do that. And so that's kind of the hierarchy, how it's done here. Just summarizing here, I think it's a pretty user-friendly, useful tool for the end users. It's literally a black box. All they need to do is fit in the 3 new runs that they ran for 9 time steps and can use it. There are also variants for other components, specifically for the ocean. So the framework, the testing framework for the ocean is quite different. This is all published. If it interests you, there are only, I think, 7 or 8 variables we look at, but we use actually the spatial fields for that. So that's a different setup that I'm not going to talk about. But what I will talk about is now 2 directions that are still kind of work in progress, and we are looking into potentially making this a little bit more useful. So now that we have the tool that actually works really well, we have some new challenges. So if we get a fail, what do we actually do about this? So this became very prominent when porting the CSM code to one of the other DOE lab computers, which, for all we know, these are amazing HPC systems. So it's of course tricky to say, no, we can't run the model there, or it gives systematically different results. So, but we got consistently fail. So we were really trying to figure out what was going on. And it took several months. I think they were at the end 10 software engineers involved trying to figure out what was going on, major headache. And it turns out the thing that was different was a compiler flag, a fuse multiply add. If you don't know what that means, basically it means instead of doing multiplication and addition as 2 subsequent steps, you do them together. It's amazing how that could potentially, it's clearly an indication of the somewhat numerical sensitivity of these models, but I guess that aside, it turns out that really changes the output in a way that we can pick up. So good thing to be aware of that, I guess. And yeah, keep that in mind. But the problem here was that size and the complexity, why this took so long to figure out what was actually the origin here, is this code is so long, big and complex, it's very difficult to identify where it is. So people would really like a tool that tells you if there's a fail, and not only just telling you there's a fail, but then points to where in the code or which part of the code actually interacts or was the culprit in the first place that likely caused this divergence. So again, this was the last part of the thesis. What he has been working on is, let's compare this failed ensemble to the failed simulations to the ensemble simulations. And of course, once we're in that space, we can start to create many more runs because we really want to know what's going on here. And turns out we actually worked with runs at time step 1. Already at time step 1, you can see what the difference is. So we developed a tool where we can basically use a fancy logistic regression to see which of these variables are the ones that are most affected, because ideally we'd like to put some runtime instrumentation in to actually see what's going on here. And what Dan did, he pruned the whole source code and passed it and represented everything as an abstract syntax tree. Then you can then turn into a directed graph to represent the entire CSM code base here. So just to give you an idea of what that looks like, yeah, that big mess here, that red thing with the blue dots, that's actually just a small part of the universe of CSM. That's what it made me think of. Yeah. And then the idea is that you do things like static slicing based on the information that you have, which variables were affected, that you can bring this down and say, well, what is actually the subgraph that is truly affected? And I won't be going into any details here, but just showing you a little bit what the idea here is. So again, we want to put in runtime instrumentation in the right spots in the code to see what's actually going on. And you can see here, we can basically use tools here for thinking about node importance and these type of things, and then place them strategically where we say within all these communities, what are the critical nodes, and figure it out, and then iteratively do that and kind of narrow the problem space down further and further. And this is, in this specific case, was the last thing you can narrow it down to, and that's pretty helpful because then you know exactly which modules are actually affected, and the IT expert can then work a little bit more directed, what part of the compiler settings or what could actually be at the origin of this here. All right, so almost done here. So we're going to look a little bit here. We have about less than 5 minutes left. Looking at the statistical details of the ECT. So I've mentioned that before. What's nice about it is we can frame that whole framework in completely, we can view it through random variables. That means we can derive the theoretical properties of it. We don't have to go through all these details. Again, this is all published if it interests you, but I'll recall here what that testing framework looks like. So we have all these individual steps. And if you think about that differently, you can all think about this as characterize this. We start off with a normal variable, and then we have Bernoulli setups that can be expressed through binomial distributions. And what's nice about that is exactly that we can derive that false positive rate. And if you tune some of these other things, and let's say you want to be extra conservative, you want the false positive of 0.01, you can change some of these parameters and play with this here. And one interesting thing that we noticed is that systematically, our false positive rate empirically, if we ran this, we do this in these scenarios, where we use the sample covariance from these 200 plus variables, and then actually we treat that as true, so we can really test the properties of our estimators. And there's an interesting statistical effect here that you can see. So these are the eigenvalues. And again, the eigenvalues are tightly connected to the variance of these PC scores. So we can directly link this. So this is a key part of our theoretical framework. So we want to make sure we actually can estimate this, right? And if you zoom in here a little bit closer, this is just reframing it as 0 is looking at how do they change as a function from the truth. You can see there's a systematic bias and overestimation in the early eigenvalues and an underestimation in the lower ones. So there's surprisingly little about that in the literature, but we did somewhat dig it up and have a better understanding now why that happens. It's a result of having a too small sample here. Also, what you see here, these were samples of size 200. So what we have done is a pretty systematic investigation as a function of ensemble size, how large we need these ensembles to push to get actually to make sure our estimators are robust. And what you can see here, I apologize, this is a little bit small here, but if you go through the columns, that's increasing the sample size, and the different rows, the first one is using that sample covariance. That's what normal PCA does. You just take the sample and use that. And you can see, if you just look at the first row, that these estimates get more and more stable once we push the ensemble size. And what you see in the second, third, and fourth row are alternative estimators. So those are ways that help us make a more robust PCA or in general sample covariance estimates. The first one is the Dorit-Wolf estimator. The third row is covariance thresholding and using sparse PCA. This is basically where we penalize, similar idea to last, where we penalize the coefficients in the basically how many of the original variables we use here. And you can see, so this, especially thresholding and sparse PCA does quite a bit better. And this will be my last slide here. So you can see how do they actually behave in terms of false positive rate here. So that blue line is the theoretical false positive rate at 0.34. And the red one is somewhat what people asked us to do, the 0.5. And you can see in small ensemble sizes here, using a naive sample estimate is suboptimal in terms of sticking to your false positive rate here. And once, this is actually a pretty interesting theoretical problem, but if you can run large enough ensemble, it clearly doesn't matter. So if you can really push up the ensemble size, nothing that would need to give you a headache. All right, so with that, thank you. There's a bunch of references.
Thank you, Dorit. Any questions for Dorit?
Hey, Dorit, that was fascinating. 9 steps. You actually commented that there was a process that only activated the 9th step. But there are actually quite a few processes that don't. There's emergent phenomena in the climate system. So I'm wondering, whether even 1 year is enough when you actually go to the full coupled system. Like, for example, we have polynomials that take a century to start developing their cycle. So, I appreciate that that's a hard answer. You can't answer that because you haven't run an ensemble with that, in this framework yet. But I am wondering if you could actually apply what you're doing to unit testing, where it solves the outer sample problem, where you can just say, let's throw random numbers at parts of the code. So you did it for the atmosphere, but you could do it for smaller parts and apply your statistics and your testing on the code as opposed to the model.
So I'll try to answer your first question first. So in terms of these emergent phenomena, clearly, we are all aware of that that's the case. So I think that when we started this, we actually, just to let you know, we put in special permission to run, I think, 1,100 year runs or something crazy. That was, like that. But it turns out anything people could think about, it doesn't mean you would truly see it, but there is a signature in these first 9 time steps. So I'm not obviously saying this from a scientific point of view. It was probably as much a surprise to me and maybe anyone else as your question indicates. And the second question, in terms of passing the code, so the problem is sometimes it's truly that the code is changed, but usually, like the fuse multiply add is not, so that's why unit testing probably isn't the right thing, or obviously unit testing is super useful, but in this specific context is certainly not the full answer. It's something in the heterogeneous aspect of the computer environment, like a compiler setting. So it's not the code per se, it's the interpretation of the code. So that's something unit testing we wouldn't catch. So, yeah.
Maybe we'll take a question online and then come back to the room. So, Judith.
Hi, Dorit. Thanks so much for your talk. So I'm not sure if I missed something, but if you look at a long control simulation or the large ensemble with CSM, what UFs or PCs do is they pick up the patterns of dominant variability. And so I do understand that this is a very nice way to look at if 2 different models are drawing from the same simulation or not. If you come to these short time steps, a few time steps or the initialized problem, what UFs do, they actually find the patterns of maximal growth, of error growth. And those are very, very different from the patterns of internal variability. In particular, in numerical weather prediction, you want to have maximal error growth to get a realistic representation of your uncertainty. And so I'm very confused why you can run only for a few time steps and get those patterns of natural variability when I would expect you would get maximal growth patterns, something like singular vectors or, you know, some projection onto those. Thank you.
Well, I can only second. I was very surprised myself. I would like to state that we are not making any claims to correctly quantify uncertainty. All we are saying is there's something in this pattern that can be distinguished, that is distinguishable. And I think that's because we do this in this PCA framework, and it is very sensitive to how variables interact, and surprisingly so. So it's somewhat a different question. If you would say, is this some kind of true representation of the underlying uncertainty? Who knows, you know, and of course all these other questions. But what is clear is that a lot of these phenomena that maybe manifest themselves much in more obvious ways later down, they're already somewhat present early on.
Could I just ask one more clarification? So how do you set up these 9 time step or 1 time step ensembles?
We just ran it out. So in the beginning, we tried all. We wanted to see how far, we know in the 1 year we could detect a lot, and then we just pushed it shorter. How long does it still work? And it turned out the 9 time step works. Again, I'm not making any science claim. I'm just saying our classification in terms of is it a pass or fail in the right conditions works.
Great, thanks, Steve.
Yeah, it was a beautiful talk. I just have a really naive question. If you take one of the PCAs with the lowest variance, so that means every single real simulation gets the exact same value. But then if you port it somewhere else and it gets a different value, wouldn't that be wrong? But you're saying it's okay.
So just to clarify, we are cutting them off, so we just use the first 50 for the actual testing framework. So if you port it somewhere else, if you say there's something legitimate happening that you believe the whole multivariate structure changes, then of course you would have to redo that. But otherwise, all we are assuming.
But sorry, if the 200th thing gets messed up, you're not looking at that, right?
Say that again.
If the 200th PCA gets messed up, is different.
No, we are not looking at that.
But shouldn't, if all the other simulations get it to be 1.4 and this new simulation gets it to be 2, shouldn't that mean it's wrong? Even if what I'm saying, even the variance in that PCA is very, very small for real simulations, shouldn't the, maybe I'm just missing something, but that makes sense. Okay, forget it then.
Maybe we can talk offline because it doesn't fully make sense to me what you're saying. Yep.
Any other questions for Dorit? Yeah, go ahead.
Thanks. I want to ask about your soil hydrology example, because of course I would expect after 9 time steps you can't detect anything from the land, but I would also think you would need longer than a year. So I'm just wondering if you could use what you've learned from this to inform how long we would need to detect changes in the land model, and maybe how that relates to spin up time for ensembles and getting to equilibrium.
Yeah, so that's a good question. So we were working a lot with the land modelers because we thought we need also a different kind of setup similar to the oceans where this wouldn't work. But this was literally the only counterexample we could find and it really wasn't worth trying to put something in the land model specifically. So again, it was very surprising how changes in the land model actually do somehow are reflected in the atmosphere output variables.
Thanks.
And it's definitely visible, this specific one with the, it's a pretty strong crank up, but it is very visible in the 1 year runs.
And is that true about the ocean also? I see that you have a...
No, the ocean doesn't work like that at all.
Okay.
This is really a fundamentally different problem because we don't have a lot of variables. So I think it looked at in the oceans were only 7 variables. I might have that wrong, like ±2. And there we actually really want to use the spatial fields because what we saw in the ocean is that sometimes things go wrong in very localized areas, and there, if you do global averaging, you destroy that signal.
Right.
So it's a totally different story. There's a whole paper.
Right.
This one is just on the ocean, which is a really different setup than this one.
Okay. So there, do you take other EOFs or different types of EOFs?
We don't do any
EOFs.
components
Okay.
there. We actually use a spatial framework where we look at the variability
Locally.
location-wise.
Okay.
Yeah. Because if you don't do that locally,
Right.
it doesn't work.
Yeah.
I can't remember. I think a year or something like that. Much longer. Yeah. Maybe even 2 years ago. I think we tested it quite a few years. Sorry, this is a while ago now. I don't remember. But we have in the paper, we have some pretty nice testing where it shows the performance as a function of how long you run it. And you're absolutely right. There is certainly not the 9 times steps, years. No. What kind of PCA?
What type?
Yeah, so there were in the last slide. So we use the kind of trivial implementation. Oops, let me just go back here. Here we have all the things written out. So all these different rows that represent. The first one is like the plain vanilla PCA, where you use the sample data to come up with the covariance, and the other ones are alternative. So the last one is fast PCA, and then the Dorit wolf is basically a regularizer. Yeah. Yep. And thresholding. Say again.
Sorry. I was wondering if you accounting for, non-Gaussian covariance spaces would make a difference.
So that we do, of course, we did very careful testing on that. But
Yeah, I imagine.
We worked with these globally average quantities. These are actually dead on normal, what can we say? Central limit theorem, it actually works. Who would have thought?
For the ocean.
No, not for the ocean.
If you're doing locally. Yeah.
Maybe appreciate the oceans in different ways.
We have a couple of more minutes. Any other questions? Yeah.
Well, I'm sorry if I missed it. So, but let's say changes in answer variability. Is it something that you worry about in here, or this is something that is just not a problem? The changes, in flags or compilers, won't affect it, because you say you run this only 1 year, even 9 time steps. Thank you.
I'm sorry, so did you say changes in
comparison? For example, changes in natural variability, like ENSO.
ENSO, okay.
Yeah. So is it something that is just not a problem here, or?
I guess not is the answer. Like again, as people when they ask exactly the kind of question when we start working on this, like how about different modes and all these type of things, and I guess it doesn't matter. Yeah. So obviously we are not running the model differently. All we are testing here is saying we are running the model in a different computing environment, or what is actually most commonly done is people try to optimize the code, so they make these kind of changes that they think it shouldn't change anything. And then they do this. So we are only talking about running otherwise everything the same, other than a different environment. So we are not. You might be right. It could be that there are some things that don't manifest themselves until much later, and that we don't pick up. But we could not. If you think you have a counterexample, feel free to bring it to the computational group. I think they're all like an open challenge. That's why we have done 100 tests, I guess.
Well, I don't know.
Yeah.
Well, it's just having correct variability of answer by like modeled by climate models is still kind of ongoing issue. So
I'm highly aware of that. It's clearly, but this might just be a slightly different question, really.
Okay, thank you.
Thank you. I think, yeah, thank you again. Great talk to it. Really interesting.